Welcome, curious dreamer, to the Sleepy Scientist. You've made it through your day, maybe even a very long one, and now it's time to unwind, slow down, and drift off to a quieter place. Tonight, we're taking a gentle journey into one of the most misunderstood wonders of the cosmos, the black hole. But don't worry, this isn't the dramatic sci-fi kind of black hole that gobbles up spaceships and slings planets around like popcorn. No. The black holes we're meeting tonight are the real ones, calm, quiet, and astonishingly well-behaved for something that literally bends space and time. As you settle in, maybe you're wrapped in a blanket or listening with your eyes already half closed. Wherever you are, on a couch, in bed, or floating in your own little corner of the universe, I'd love to know where you're tuning in from and what time it is for you. Drop it in the comments if you feel like it. It's always lovely to see how far this sleepy little ship sails. And while we're gently drifting toward the event horizon of relaxation, a kind reminder: if you enjoy these nighttime voyages, tapping the like button or subscribing helps the channel float a little further. It's like tossing an extra pillow under the head of the algorithm. Soft, supportive, appreciated. Now I'll try not to make things too interesting, but if by some chance the mystery of black holes does happen, to keep your eyes open a little longer, well, at least you'll learn something truly cosmic along the way. So take a deep breath. Let it go. Let the stars above you and the science around you lull your mind into a gentle stillness. Our story begins in the dark, right where the black holes sleep. Imagine, if you will, a place in the universe where the laws of physics start to bend, wobble, and generally behave like they've had a long day and just want a nap. A place where light itself, usually the fastest thing we know, gets trapped, never to escape. This is the curious realm of black holes. But what are they really? Not the cartoonish swirling portals to oblivion you might have seen in movies, but something far more subtle, strange, and dare I say peaceful. At its core, a black hole is a region in space where gravity has won. Everything in the universe is a bit of a tug of war between outward pressure and inward pull. Stars burn with nuclear fusion, creating energy that pushes outward, while their immense mass pulls inward with gravity. But when a massive star runs out of fuel, the fusion stops, the outward pressure vanishes, and gravity wins. The star collapses in on itself, folding tighter and tighter until it becomes something incredibly dense and tiny. A singularity wrapped in a cloak of no return called the event horizon. Let's unpack that a bit. The singularity is, quite literally, a point of infinite density. It's where all the matter that once made up a huge star gets squished into an unimaginably small space. It's the ultimate space-saving hack, except instead of decluttering your closet, it compresses entire suns into a speck. Around this singularity lies the event horizon, which you can think of as the black hole's outer shell. It's not a surface like a planet's crust, but more of an invisible boundary. Once anything crosses it, light, matter, bad space poetry, it's not coming back. Now here's the twist. Black holes are actually some of the simplest objects in the universe. According to general relativity, a black hole can be completely described by just three things: its mass, its spin, and its electric charge. That's it. No matter what went into the black hole, a star, a planet, your favourite left sock, it's all reduced to those three properties. There's even a name for this simplicity: the no-hair theorem. Black holes, it turns out, are cosmically bald. This might sound like they're erasing information, swallowing it up forever. That idea led to one of the biggest debates in physics, the information paradox. But don't worry, we're not diving into quantum theory right now. Just know that even in their simplicity, black holes are still stirring the scientific pot. But despite their dramatic origin stories and exotic physics, black holes are not cosmic vacuum cleaners. They don't go chasing down unsuspecting planets like space sharks. In fact, if you replaced our sun with a black hole of equal mass, don't worry, it's not going to happen. The Earth would keep orbiting just fine. A bit darker, sure, but otherwise no change in the gravitational dance. Black holes don't suck things in, they just sit there, quietly curving space. And that's what makes them fascinating. Their presence is felt not through visibility, but through influence. We can't see a black hole directly, it's black after all, but we can detect its fingerprints. When a black hole tugs on a nearby star, causing it to wobble or orbit in strange ways, we take notice. When it gobbles up gas and dust from a companion star, the material gets so hot as it spirals in that it shines brightly in X-rays. That's when the quiet giant briefly stirs. But for the most part, black holes don't do much. They don't emit light. They don't make noise. They don't pose threats unless you get extremely, and I mean extremely close, which, statistically speaking, you won't. The closest known black hole to Earth is over 1,000 light-years away. That's like being worried about a tiger when the nearest one is on another continent. Because they don't reflect or emit light, black holes are invisible against the fabric of space. It wasn't until 2019 that we actually saw the shadow of one, thanks to a global collaboration called the Event Horizon Telescope. They captured the silhouette of a supermassive black hole at the center of the M87 galaxy, 55 million light-years away. And it wasn't some gaping hole of doom. It looked like a glowing donut. Peaceful, dignified, hungry maybe, but in a laid-back way. The idea of something so powerful being so calm is strangely comforting. In a universe full of exploding stars, chaotic galaxies, and speeding particles, black holes are quiet. They're the strong, silent type. The introverts of the cosmos. They don't start drama, they don't chase fame. They just sit at the crossroads of gravity and geometry, being themselves. And perhaps most surprisingly, they obey the rules. They fit neatly into Einstein's equations. They follow thermodynamic laws. They even have entropy, a measure of disorder, which gives them a kind of temperature, albeit one so cold it's practically absolute zero. It's like discovering that the universe's scariest monster is actually an orderly librarian who whispers and files things alphabetically. So next time you hear the words black hole, don't picture a violent devourer of worlds. Think of a quiet ripple in space, a place where time slows, light rests, and matter finds its final silent home. Think of gravity doing its job with the seriousness of a monk and the patience of a glacier. Black holes may be the endpoint for matter, but they're far from chaotic. In fact, they may be the most peaceful residents of our cosmic neighborhood. They don't scream for attention. They don't sparkle. They simply exist, calmly, invisibly, and eternally. Let's imagine a star, a big one, not the modest, middle-aged ball of fusion that is our sun, but something far more massive. 10, maybe 20 times the mass of the sun. It shines brighter, burns hotter, and lives faster. These colossal stars are like the rock stars of the cosmos, loud, brilliant, and doomed to a dramatic end. This is where black holes are born. You see, stars are all about balance. At the core of a star, nuclear fusion converts hydrogen into helium, releasing enormous amounts of energy. This energy pushes outward, creating pressure that holds up the star against the inward pull of gravity. It's a delicate equilibrium like two equally matched teams in an eternal tug of war. The outward force of fusion keeps gravity from pulling the star into itself, while gravity keeps the whole thing from flying apart like cosmic confetti. But fusion doesn't last forever. Eventually, a massive star runs out of fuel. It starts burning through heavier and heavier elements, moving from hydrogen to helium to carbon and so on, until it gets to iron. That's the dead end of stellar fusion. Iron doesn't yield energy when fused, it consumes it. So when a star's core fills with iron, the party is over. Fusion stops, and gravity, long kept at bay, suddenly finds itself unopposed. Now, remember, we're talking about a star many times the mass of our sun. That's an immense amount of material being pulled inward in a very short time. The core collapses in milliseconds, and the outer layers fall in too, creating a dramatic implosion. But like a trampoline flinging back a bowling ball, this inward crash can cause a rebound, an enormous shockwave that blasts the outer layers into space. This is what we call a supernova. Supernovae are among the most violent events in the universe. They shine with the brightness of entire galaxies and scatter elements like gold, uranium, and iodine into space, the very atoms that later make up planets, plants, and a people. Yes, you have stardust in your bones, and your molars may have come from a dying star. Kind of poetic, isn't it? But for the core that remains, there are only a few possible fates. If the leftover mass is under about 1.4 times the mass of the Sun, it can become a white dwarf, a dense Earth-sized ember that slowly cools over billions of years. A bit more massive, and it becomes a neutron star, an object so dense that a teaspoon of it would weigh more than a mountain. But if the core's mass exceeds a certain threshold, roughly 2 to 3 times the mass of our Sun, gravity overwhelms all known forces. Not even the pressure from neutrons, packed together as tightly as possible, can resist it. The core collapses completely. There's no more pushing back, it becomes a singularity, a point of infinite density, and the black hole is born. No explosion, no flashing sign, just quiet collapse. One moment it's a star, the next, a shadow. This kind of black hole is called a stellar mass black hole, and it's the most common kind we know of. They typically weigh between a few and a few dozen times the mass of the Sun and are scattered throughout galaxies like cosmic fossils. We can't see them directly, but we infer their presence by how they interact with their surroundings, especially if they're in a binary system with a companion star. In these binary systems, the black hole's gravity can pull gas from its partner. This gas spirals inward, forming an accretion disk that heats up to millions of degrees and emits powerful X-rays. That's how we spot them from their appetite. Like a polite guest who only becomes noticeable when they start eating all the snacks. Some stellar mass black holes are the quiet type. They have no close neighbours to steal matter from and drift through the galaxy in near total darkness. These rogue black holes are essentially invisible, unless they pass in front of a distant star, in which case they can briefly warp and magnify the starlight behind them, thanks to their gravitational field. This effect is called gravitational microlensing, and it's one of the clever ways astronomers detect the undetectable. Now, let's take a moment to think about just how extreme black holes are. Imagine compressing the Earth down to the size of a marble. That's the kind of density we're talking about. For the Sun to become a black hole, it would need to be crushed into a sphere just 6 kilometers across. That's smaller than a city, but it would still hold all the Sun's mass, and the gravity at its surface would be a bit intense, to say the least. And yet, as wild as that sounds, black holes formed from stars are remarkably stable. Once they're born, they don't change much. They don't explode or decay, at least not for trillions of years. They simply sit there, bending the space around them, invisible and content. It's oddly peaceful, really. From fiery birth in the heart of a supernova to quiet existence in the galactic outskirts, black holes are like cosmic monks. Having seen the heights of drama, they now sit in serene silence. And contrary to popular belief, you wouldn't feel anything particularly unusual when crossing the event horizon, assuming the black hole is massive enough. If you were to fall into a stellar mass black hole, yes, you'd be in trouble. Gravity increases so sharply that the tidal forces would stretch you into what physicists affectionately call spaghettification. But for a supermassive black hole, the event horizon is so far from the centre that you might not notice crossing it at all. You'd just drift in, quietly, forever. So next time you gaze up at the stars and wonder about the dark spaces between them, remember that some of the universe's most dramatic stories end not with chaos, but with stillness. Black holes are born in fire, but they live in silence. They are the quietest of cosmic objects, the final resting place of massive stars. From brilliant life to invisible slumber, they are, quite literally, sleeping giants. Black holes have an intimidating reputation. The name alone conjures up images of bottomless pits in space, slurping up everything in sight like a cosmic vacuum cleaner gone rogue. But let's take a breath and get to know them a little better, because despite all the dramatic PR, most black holes are surprisingly well behaved. In fact, many of them are, quite literally, doing absolutely nothing. You see, not all black holes are gorging themselves on nearby stars or swirling clouds of gas. Most of them are what scientists call quiescent, which is a fancy way of saying quiet. They're just there, sitting peacefully in the dark, invisible, causing no fuss. You could fly right past one, assuming you weren't on a collision course, and you'd be none the wiser. No screams, no flashes, no warning signs. Just a quiet pocket of gravity, minding its own business. It might help to think of black holes not as cosmic predators, but more like sleeping giants. Immensely powerful, yes, but asleep still and entirely non-threatening unless provoked. A black hole won't chase you. It won't suck in everything around it like a bathtub drain. Space is vast and black holes are small by comparison. Unless something gets very, very close, it won't be affected. Here's the thing, for a black hole to do anything flashy, like emit X-rays, shoot out jets of energy, or cause dramatic gravitational effects, it needs fuel. It needs matter nearby that it can pull in. But most of the universe is empty. Even in the crowded parts of galaxies, space is still mostly, well, space. So while a few black holes have front row seats to dramatic events, most of them are sitting in the back, quietly contemplating the void. When a black hole does find a snack, say a passing cloud of gas or a neighbouring star that strays too close, it can flare up for a while. The material gets caught by the black hole's gravity and spirals inward, forming a hot, glowing accretion disk. This disk isn't inside the black hole, it's just outside the event horizon, where the material heats up from friction and releases energy, sometimes a lot of energy. But this isn't the black hole itself glowing, it's the dinner plate. The black hole remains invisible. What we're seeing is the frantic last moments of matter heating up as it spirals toward oblivion. It's a bit like watching steam rise from a hot cup of tea. It's a sign something interesting is happening, but not the main event itself. Now, there are exceptions to this sleepy behaviour. Some black holes, particularly the supermassive ones at the centres of galaxies, go through energetic phases known as active galactic nuclei. These are the black holes that power quasars and blazars, blasting out jets of radiation and plasma that span thousands of light years. It's like the black hole wakes up, has a bit of indigestion, and starts belching beams of energy across the cosmos, but even that excitement is short-lived in cosmic terms. After a few million years, a blink of an eye to the universe, the fuel runs out, the light show ends, and the black hole goes back to sleep. For the vast majority of their lives, black holes are dark, quiet and undetectable. They don't shine, ray reflect or glow. We only know they're there because of how they affect nearby matter. If a star is orbiting something invisible, and the math says that invisible thing must be several times more massive than the Sun, and fits into a very small space, well, congratulations, you've probably found a black hole. This quiet nature makes them both fascinating and frustrating to astronomers. Detecting a black hole is a bit like trying to find a completely silent cat in a pitch-black room, using only your knowledge of how gravity works. And just like cats, black holes don't care about being found. They'll just sit there, purring, metaphorically, whether you're watching or not. Interestingly, black holes are not entirely black. In the 1970s, physicist Stephen Hawking proposed that black holes actually emit tiny amounts of radiation, now called Hawking radiation, due to quantum effects near the event horizon. This means that over incredibly long timescales, black holes can slowly lose mass and evaporate. But don't worry, they're not going anywhere anytime soon. A black hole with the mass of our Sun would take roughly 67 years to evaporate. That's a number so big, it makes the age of the universe, just 13.8 billion years, look like a coffee break. So if you're picturing a black hole as some terrifying, all-consuming force, it might be time to adjust the mental image. Think of them more like lighthouses that have turned their lights off, still standing, still solid, but not currently doing much. Their presence shapes the space around them, gently influencing nearby stars and gas. They are landmarks of gravity, strong, silent and stable. In fact, if you could somehow orbit a black hole at a safe distance, you'd have one of the most stable rides in the universe. You'd feel the immense pull, sure, but if you were far enough away, it would be no different than orbiting any other massive object. You could circle it for eternity, admiring the black void in the centre of your view, knowing that nothing else in the universe could affect you as calmly and predictably. And while we often focus on their destructive potential, black holes are in many ways protectors of information. Every bit of matter or energy that falls into one adds to its mass, changes its spin and contributes to its gravitational fingerprint. It's all recorded somehow, even if we can't yet decode what it means. Some physicists believe the event horizon itself stores this information like a kind of hologram. It's the cosmic equivalent of a diary written in gravitational ink. There's something almost philosophical about how quiet and contemplative black holes are. They don't move fast, they don't shout, and they don't fade easily. They endure. For billions upon billions of years, they persist in the galactic dark, unaffected by passing trends, shifting stars, or exploding nebulae. They are the calm eye in the cosmic storm. So the next time you picture a black hole, don't think of it as a monster. Think of it as a sleeping sentinel, a relic of a stellar life now resting peacefully. It won't chase you. It won't reach for you. It will just be there. A wrinkle in the space-time, quietly keeping watch over the silent starry dark. Let's scale up. We've talked about black holes formed from dying stars, stellar mass black holes that weigh a few times more than our Sun, and tend to keep to themselves in quiet corners of the galaxy. But there's another class of black holes, bigger, older, and quite possibly more mysterious. They sit at the centres of galaxies, including our own. These are the giants, the supermassive black holes. And when we say supermassive, we mean it. These behemoths range from millions to billions of times the mass of our Sun. Imagine a black hole that could swallow not just one star, but every star in the solar system and still have room for seconds. The one at the centre of our Milky Way, known as Sagittarius A, pronounced A star because astronomers enjoy confusing punctuation, weighs in at about 4 million solar masses, and that's considered modest by cosmic standards. Here's the fascinating part. Despite their monstrous size, supermassive black holes aren't destructive by default. In fact, our entire galaxy calmly orbits around one. There are no apocalyptic gravitational effects, no galactic panic attacks. Just a stable core, quietly anchoring the spiral arms of the Milky Way like a cosmic keystone. But how did these supermassive black holes get so, supermassive? That is a question astronomers are still trying to answer. Stellar mass black holes are straightforward. Star goes boom, core collapses, black hole forms, but there's no single star massive enough to collapse directly into a billion solar mass black hole. So how do we go from relatively petite black holes to these gargantuan anchors of galaxies? There are a few theories. One possibility is that early in the universe, there were so-called seed black holes, either from massive stars or from direct collapses of giant clouds of gas. These seeds then grew over time, gobbling up matter and merging with other black holes, slowly climbing the cosmic food chain until they reached supermassive status. But here's the tricky part. Some supermassive black holes existed very early in the universe's history, just a few 100 million years after the Big Bang. That's not a lot of time to bulk up to billions of solar masses, even by black hole standards. So researchers are still hunting for explanations. Perhaps some grew faster than expected. Perhaps the early universe was more generous with its cosmic buffet. Or maybe we're missing a key piece of the puzzle entirely. Whatever their origin, once these giants settle into the centres of galaxies, they tend to stay there. They sit at the heart of everything, gravitationally influencing stars, gas and dark matter over vast distances. They're like the quiet elders of the galaxy, stoic, enormous and unmovable. And while most of the time they're dormant, barely interacting with their surroundings, there are moments when they light up. When a supermassive black hole starts feeding, it becomes what we call an active galactic nucleus, AGN. Gas and dust spiral into the black hole, forming a hot accretion disk and creating jets of energy that can stretch for thousands or even millions of light years. These jets aren't made of matter falling into the black hole, but rather material being ejected along its magnetic poles at nearly the speed of light. It's like the black hole has indigestion and vents it out into the universe. Some of the brightest objects in the universe, quasars, are powered by these active black holes. Quasars can outshine entire galaxies, even though they're powered by an area not much larger than our solar system. Imagine something the size of our neighbourhood blasting out more light than 100 billion stars combined. It's an astronomical overachiever. But again, these active phases don't last forever. Eventually the black hole runs out of material to feed on, the fireworks fade, and the quasar goes quiet. The galaxy continues to orbit peacefully, the black hole back in hibernation, like a bear that finished a very large meal and has gone back to sleep for another few million years. Back to our own galaxy, the Milky Way. Sagittarius A is, by all accounts, quite tame. It's not currently feeding on much, and it hasn't been active in our lifetimes, or really, in the lifetime of human civilization. But astronomers believe it has stirred in the past. Echoes of ancient activity are visible in the form of massive gamma-ray bubbles above and below the galactic plane, giant ghostly footprints left by a once feasting giant. To truly see Sagittarius A, we needed a global effort. In 2022, astronomers from the Event Horizon Telescope collaboration released the first image of our galaxy's central black hole, not a photo in the traditional sense, but a carefully reconstructed view of its shadow. A glowing, donut-shaped halo of gas surrounds a dark centre, where light can no longer escape. It's not a Hollywood wormhole. It's fuzzy, blurry and orange, but it's real. Proof that something vast, invisible and powerful lies at the heart of our galaxy. And here's the quiet wonder of it all. These black holes don't just sit at the centre of galaxies, they shape them. The presence of a supermassive black hole seems to influence star formation, regulate the flow of gas, and affect the overall architecture of a galaxy. Some studies suggest a kind of symbiotic relationship. Galaxies and their central black holes grow together, each influencing the other over billions of years. It's not a top-down dictatorship, but more of a quiet agreement. You build the stars, I'll keep things anchored. So while it might seem odd to describe a supermassive black hole as peaceful in many ways, that's exactly what they are. Their very presence brings order. They keep galaxies coherent. Without them, the swirling arms might unravel. Their gravity is a silent sculptor, holding together the stellar stage on which galaxies perform. They are not to be feared, but to be respected. Enigmatic engines of gravity, pulsing faintly at the heart of creation. They're reminders that even the universe's most powerful forces don't always shout. Sometimes they whisper, sometimes they sleep. So the next time you look up at the stars and see the soft curve of the Milky Way arching across the night sky, remember that at its centre, 26,000 light-years away, there's a black hole, 4 million suns worth of mass curled into a silent sphere, not tearing things apart, not glowing with fire, but simply existing, anchoring, waiting, resting, a true sleeping giant. Picture yourself drifting slowly through the cosmos, weightless and serene, when suddenly you notice something odd. A distant star has started to spiral, circling an invisible point in space, like it's caught in a cosmic whirlpool. It's not being torn apart, not yet, but it's clearly in the grip of something powerful. That something, of course, is a black hole. But what's happening to the star? What is life like around a black hole? And what really goes on in that mysterious region of space? Despite their secretive, shadowy reputation, black holes don't exist in total isolation. While they themselves are invisible, they often make their presence known by their effect on the matter surrounding them. And that effect can be dramatic. Let's start with the accretion disk, a glowing, swirling platter of gas and dust that sometimes surrounds an active black hole. This disk forms when material, often from a nearby star or gas cloud, falls under the black hole's gravitational spell, but instead of plunging straight in, it starts to spiral, pulled by gravity but also conserving angular momentum. Picture water circling a drain, only the water is superheated plasma and the drain is a tear in the fabric of space-time. As the gas spirals inward, friction and compression heat it to extreme temperatures, millions of degrees. At these temperatures, the disk can emit intense X-rays and even gamma rays, lighting up telescopes across the electromagnetic spectrum. So while the black hole itself remains dark, the region around it can be dazzlingly bright, like a campfire illuminating the mouth of a cave. But it's not just hot gas that makes life around a black hole interesting, it's also the wild physics. Take gravitational time dilation, for instance. This is a strange prediction of Einstein's general relativity. The closer you are to a massive object, the slower time moves for you compared to someone farther away. Near a black hole, this effect becomes extreme. If you parked a spaceship just outside the event horizon and hovered there, ignoring the engineering problems that would come with that, time would pass much more slowly for you than for your friends back home. It's not just science fiction. This time-warping effect is real, and it means that if you could somehow orbit a black hole at just the right distance, you'd experience a kind of time travel into the future. Hours for you could be years for everyone else. In fact, this is one of the few science fiction tropes with real science behind it. So if you've got a deadline coming up and need a cosmic excuse, well, there's your out. Of course, getting too close to a black hole has its risks. Venture beyond a certain point, called the event horizon, and escape becomes impossible. This isn't a physical surface, but rather a boundary. Once you cross it, there's no coming back, no matter how fast you move. It's the cosmic equivalent of you break it, you bought it. Only instead of breaking something, you've just entered a region of space where physics takes a coffee break. And what happens if you do fall in? Well, it depends on the size of the black hole. If you're unlucky enough to fall into a stellar mass black hole, the gradient of gravity from your head to your toes becomes immense. This difference in gravitational pull is so extreme that it would stretch you lengthwise and compress you sideways in a process scientists charmingly refer to as spaghettification. Yes, that's the actual term. The universe has a sense of humour, apparently. But if you were to fall into a supermassive black hole, like the one at the centre of our galaxy, the story's a bit different. The event horizon is much farther from the singularity, and the gravitational gradient is far more gentle. You could, in theory, cross the event horizon without immediately being torn apart. You'd still never escape, of course, but your last moments might be eerily calm. Let's float back out for a moment to the area just outside the event horizon. Here, in a region called the ergosphere, if the black hole is spinning, weird things start to happen. Due to the immense angular momentum of a rotating black hole, space-time itself is dragged along with it, a phenomenon called frame dragging. If you were caught in the ergosphere, you'd be forced to spin along with the black hole. You couldn't stay still even if you tried. It's like being in a cosmic whirlpool where even light can't just hang out without being carried along. Scientists theorize that this effect could allow for energy to be extracted from a spinning black hole, using a method called the Penrose process. It's all highly theoretical and involves incredibly complex mechanics, but the idea is that under just the right conditions, you could steal a little bit of a black hole's rotational energy. It's kind of like tipping a sleeping giant and managing to siphon off some of its strength without waking it up. Outside the swirling chaos of the accretion disk, life gets much quieter. Black holes don't broadcast their presence unless they're actively feeding. A black hole with no accretion disk is practically invisible, silent and dark, blending into the blackness of space. There could be thousands of these quiescent black holes in our galaxy alone, just drifting among the stars, completely undetectable unless they interact with something. So what does life look like around a black hole, cosmically speaking? Well, it's not all destruction and chaos. In fact, some of the most stable and fascinating systems in the universe involve black holes. Binary systems where a black hole orbits a star are not uncommon. The black hole may gently draw material from its companion star, creating a glowing disk. In some cases, the system emits regular bursts of X-rays pulsing like a heartbeat. Even more exotic are systems where two black holes orbit each other. These binary black hole systems are rare but incredible. As they spiral toward each other over millions of years, they emit gravitational waves, ripples in the fabric of space-time. These waves were first detected in 2015 by the LIGO Observatory, confirming a century-old prediction from Einstein. It was like hearing the universe hum for the first time. These gravitational waves aren't just scientifically exciting, they're a whole new way to study the cosmos. They allow us to listen to the universe in a completely different language, revealing collisions and mergers of black holes far beyond what we could ever see with light. So yes, black holes are strange, powerful, and a bit mysterious. But around them, in the invisible spaces and glowing disks, lies a world of extraordinary physics. A place where time bends, matter glows, and gravity speaks in ripples. It's not all doom and gloom. In many ways, it's a cosmic ballet, matter spinning, energy flowing, time stretching. Life around a black hole is anything but boring. It's dynamic, radiant, and rich with discovery. And as we continue to observe these sleeping giants, we're learning that their silence is full of stories. All you have to do is listen. From a distance, black holes might seem like cosmic loners, quiet, dark, and self-contained. But if you zoom out far enough, you begin to see something extraordinary. They're not just lurking in the universe, they're shaping it. Particularly when it comes to the giants, the supermassive black holes at the centers of galaxies, their presence can influence the very structure and destiny of the galactic worlds that swirl around them. Let's begin with an intriguing observation. Almost every large galaxy we've studied has a supermassive black hole at its core. Spiral galaxies, elliptical galaxies, irregular ones, no matter the shape, if it's got mass and stars and has held itself together for billions of years, odds are good there's a black hole in the middle. That can't be coincidence. More than just coexisting, galaxies and their central black holes seem to be deeply connected. Astronomers have discovered a curious correlation. The mass of a galaxy's central black hole is directly related to the mass of the galaxy's bulge, the dense, star-packed central region. It's not a one-to-one ratio, the black hole is much smaller, but the relationship is surprisingly consistent. This suggests that black holes don't just live in galaxies, they grow with them. It's a cosmic chicken and egg question. Did the galaxy form around the black hole, or did the black hole grow inside a pre-existing galaxy? The answer is probably yes. Both, in a sense. The leading theory is that galaxies and their central black holes evolved together, influencing one another over billions of years through a process scientists call coevolution. But how can something so relatively small, the black hole is usually less than 0.001% of the galaxy's total mass, have such a big influence? The answer lies in energy. When a supermassive black hole is feeding, gulping down gas, dust, or even whole stars, it doesn't do so quietly. As material falls into the black hole's accretion disk, it gets compressed and heated to astonishing temperatures. Some of that material crosses the event horizon, never to return, but a lot of it doesn't make it that far. Instead, it's whipped around the disk, collides with itself, and releases massive amounts of energy. This energy is so intense that it can blow gas out of the galaxy altogether. We're not talking about a gentle breeze either. These are relativistic jets, blasts of charged particles travelling near the speed of light. They're launched from the poles of the spinning black hole, and they can stretch for hundreds of thousands of light years. They slice through space like cosmic blowtorches, heating interstellar gas, disrupting star formation and shaping the large-scale structure of the galaxy. This process is known as AGN feedback, short for active galactic nucleus feedback. It's one of the most important and still somewhat mysterious mechanisms in modern astrophysics. AGN feedback can regulate how many stars a galaxy forms by either heating up the gas so it can't collapse into new stars or by ejecting the gas entirely. In other words, a black hole can slow down or even halt a galaxy's stellar production. It's like a thermostat, quietly keeping the galaxy from overheating or overproducing. At first glance, it might seem odd. How can a galaxy be helped by a giant gravity-crushing void? But nature is full of these strange balancing acts. Just as forest fires can prevent overgrowth and allow ecosystems to thrive, black holes, through their energetic outbursts, help keep galaxies stable and orderly. Even in their quieter phases, black holes exert control. Their gravitational pull affects the orbits of stars in the central regions of galaxies. The stars closest to the center zip around at breakneck speeds, betraying the presence of something massive and invisible. By mapping these motions, astronomers can estimate the mass of the hidden black hole. This is how we first confirmed the presence of Sagittarius A in the Milky Way. It wasn't glowing, but the stars around it were dancing like it was the galaxy's DJ. And let's not forget galaxy mergers. When two galaxies collide, a relatively common event in the cosmic scheme of things, their central black holes spiral toward one another, gradually losing energy through gravitational interactions with stars and gas. Eventually they get close enough to form a binary system, and over time, they merge into a single, even larger black hole. These mergers release enormous amounts of gravitational waves, ripples in the very fabric of space and time. Detected for the first time in 2015, gravitational waves have opened up a new way to observe the universe. We no longer need to rely solely on light. Now we can listen to cosmic events through the tremors they send across space. And one of the loudest sounds in this gravitational symphony, the merger of supermassive black holes. What's truly fascinating is that we're just beginning to understand how black holes sculpt the universe on grand scales. Some scientists believe that the large-scale structure of the cosmos, the vast web of galaxies and dark matter filaments stretching across space, might have been influenced in part by black holes and the energy they released over cosmic time. Imagine a galactic landscape dotted with quiet volcanoes that erupt once every billion years, reshaping everything around them. Even in galaxy clusters, huge groups of galaxies bound together by gravity, central black holes play a key role. The largest galaxies in these clusters often host the most massive black holes, and their energy output helps prevent gas in the cluster from cooling and forming too many stars. Without these outbursts, clusters could become unstable, collapsing under their own density. Once again, the quiet giants provide balance. Back in our corner of the universe, the Milky Way is currently in a relatively calm state. Sagittarius A is not particularly active, but that doesn't mean it's not influencing things. Its presence keeps the central regions of the galaxy in order, its gravity subtly shaping the orbits of stars and gas. It may one day flare to life again, perhaps if a wandering cloud drifts too close or a rogue star dares to trespass. For now it rests, a cosmic anchor holding our galaxy together. Black holes, especially the supermassive ones, are not just endpoints. They're architects, gardeners, sometimes even regulators. They don't simply swallow, they shape. Their influence stretches far beyond their event horizons, touching every corner of the galaxies they inhabit. They teach us that power doesn't have to be loud. That influence can be subtle, and that sometimes the quietest forces are the ones that build the foundations of everything we see. So the next time you look at a galaxy, whether in a photograph or through a telescope, remember that at its heart lies a sleeping giant. Not a destroyer, but a sculptor, a being of gravity and silence, gently guiding the dance of stars, shaping the story of the cosmos one orbit at a time. Black holes are known for being the ultimate endpoints in the cosmic life cycle, the places where matter goes never to return. But is that really the end of the story? Are black holes eternal? Or can even these mighty invisible giants eventually meet their end? As it turns out, they can, and their demise is as slow, strange and quiet as their lives. Let's start with something surprisingly delicate: Hawking radiation. In 1974, physicist Stephen Hawking proposed a revolutionary idea. Black holes aren't entirely black. They're not completely inescapable prisons of matter and light. They actually give off a faint glow. A very faint glow. This was shocking. According to classical physics, nothing can escape a black hole, not even light. But Hawking applied the quirky principles of quantum mechanics to the area just outside the event horizon, and what he found was extraordinary. Here's the simplified version. In the strange world of quantum physics, empty space isn't truly empty. It's buzzing with energy, constantly producing pairs of virtual particles, one matter, one antimatter, that pop into existence and then annihilate each other almost instantly. This happens everywhere all the time, even in the vacuum of space. But near the event horizon of a black hole, something curious can happen. If a pair of these virtual particles appears right at the edge, one can fall in while the other escapes. The black hole loses a tiny bit of its mass to the escaping particle, which then flies off into space. To an outside observer, it looks like the black hole is emitting radiation. This phenomenon, Hawking radiation, suggests that black holes can very slowly lose mass. And if they keep losing mass, eventually they'll evaporate entirely. The key word here is slowly, incredibly slowly. A black hole the mass of our Sun would take about 1067 years to evaporate. That's a number so big it's practically useless for human comprehension. To give you some context, the universe is currently around 13.8 billion years old. That's not even a scratch on the timeline of a black hole's lifespan. And supermassive black holes, they'll take even longer, up to 100 years or more, to evaporate. That's a Google years. If your brain just gave up on trying to picture that, you're not alone. At that point, all stars will have burned out, galaxies will have dispersed, and the universe will be a vast, dark, cold sea of dust and black holes. This era is sometimes poetically called the Black Hole Era. In this distant epoch, black holes will be the last game in town. Everything else will have faded. Planets, stars, even atoms will have either decayed or drifted apart into loneliness. The black holes will be the last to go, sitting in the dark, ever so slowly losing energy, till one by one they blink out of existence, releasing a final whisper of heat. This final evaporation isn't an explosion, it's not a dramatic finale. It's more like a sigh, an exhale from an object that has spent trillions of years quietly compressing the universe's secrets. And once the last black hole evaporates, the universe will be left in a state known as heat death, or thermodynamic equilibrium. All energy will be evenly spread out. No gradients, no structure, no movement. Just cold, quiet, uniform nothingness. But let's pull back from the edge of eternity for a moment. Hawking radiation remains, for now, a theoretical prediction. We haven't observed it directly. The signal is far too faint to detect with our current instruments, but most physicists agree that the idea is sound, and it fits neatly with our best theories of quantum gravity, however incomplete those theories may be. This brings us to one of the biggest puzzles in theoretical physics, the information paradox. Here's the issue. According to quantum mechanics, information about a physical system, what particles it contains, how they're arranged, can never truly be destroyed. Even if you burn a book, the information it contains still exists in the arrangement of ash, smoke, and energy. You might not be able to reconstruct the book from that mess, but in principle the information still exists. But if you throw something into a black hole, a star, a planet, or a very unlucky spacecraft, it seems that all information about it is lost forever. And if the black hole eventually evaporates away, taking that information with it, quantum theory has a serious problem. This is the black hole information paradox, and it's been keeping physicists up at night for decades. Where does the information go? Is it encoded in the Hawking radiation? Does it get stored on the event horizon somehow, like a cosmic hard drive? Is it released at the end of evaporation? Or is our understanding of physics incomplete? No one knows for sure. Some of the brightest minds on Earth are still working on it, and the answers, when they come, may fundamentally reshape our understanding of space, time, and the very nature of reality. But while the physicists do the heavy lifting, we can marvel at the poetic possibilities. Black holes, once thought to be cosmic endpoints, may in fact be part of a grand cycle. They may not destroy information, they may just hide it in ways we don't yet understand, and their eventual demise. Not a bang, but a whisper. A final sigh from the universe's most enigmatic residents. For now, though, black holes are alive and well. Most are still in their prime, orbiting silently through galaxies, anchoring stars, regulating cosmic ecosystems. The process of evaporation is too slow to matter in any practical sense, unless you're planning to stick around for a few Google years. Even so, there's something profoundly comforting about the idea that black holes, the supposed cosmic destroyers, aren't eternal. That even the most powerful, most mysterious objects in the universe have lifespans. That everything changes, everything ends. But those endings, like the black holes themselves, are not always loud or violent. Sometimes they're silent and slow. Sometimes the universe just lets go. So the next time you hear someone talk about black holes as terrifying monsters, remember this: they are, yes, in the end, fragile. Their lives are long, yes, longer than stars, longer than galaxies, but not infinite. Even giants sleep, and even giants fade. If you could somehow drift far enough into the future, past the end of stars, past the quiet evaporation of black holes, past every blazing moment the universe has to offer, you'd find yourself in a place of unimaginable stillness. The lights have gone out, the show is over, and all that remains is silence. This, according to our best scientific models, is the long, slow final act of the cosmos. A time when black holes are not just residents of the universe, they are its last living things. Let's set the stage. The universe began around 13.8 billion years ago with the Big Bang. It was hot, dense, chaotic. Over time it expanded and cooled, stars formed, galaxies spun, life somewhere may have emerged. But nothing lasts forever. Stars, as beautiful as they are, have a finite fuel supply. Eventually, even the most stable stars, like our own sun, will burn out. In fact, roughly 100 trillion years from now, the last stars in the universe will flicker and die. This marks the beginning of what physicists poetically call the degenerate era. In this era, the universe no longer shines. All that remains are white dwarfs, neutron stars, and black holes, remnants of a more vibrant time. White dwarfs may cool into invisible black lumps of carbon called black dwarfs. Neutron stars too will go quiet, but the black holes, they'll persist. They are, after all, the most resilient structures we know. As everything else fades into obscurity, black holes become the universe's final anchors. During this vast stretch of time, occasional events may still occur. Rogue planets might drift past dead stars, white dwarfs could slowly collide in rare silent dances, but overall, it's a universe of shadows, of whispers, of things too cold to glow and too old to change. And then, one by one, even the black holes begin to die. As we explored in the last chapter, Hawking radiation predicts that black holes lose mass over time by emitting faint radiation. Large black holes evaporate slower than small ones, but given enough time, a lot of time, even the largest will vanish. Supermassive black holes, the kind that weigh billions of times more than our Sun, may take around 110 or 100 years to fully evaporate. That's a Google years. Just for perspective, that's about 1087 times longer than the current age of the universe. We call this era the time when black holes are the last luminous things in the cosmos, the black hole era. It's a poetic name for a very quiet reality, one in which gravity still rules, but with almost nothing left to pull. One in which time continues to tick, but there's no one left to count the seconds. So what does this distant future look like? Cold, dark, still. The universe has expanded so much that the remnants of galaxies are unimaginably far apart. Most atoms have long since decayed or been absorbed by larger objects. No light shines. The cosmic microwave background, the last remnant of the Big Bang's heat, has stretched into unmeasurable wavelengths. The universe is not just empty, it is quiet in a way that's hard to grasp. It's a place where entropy, the measure of disorder, has reached its maximum. There are no energy gradients left, no heat differences to power movement or life or structure. Everything that could fall apart has fallen apart. It's a state known as heat death, where the universe has achieved thermodynamic equilibrium. Not because everything is the same, but because nothing can change. And yet there's something oddly peaceful about this idea. A universe where everything is done. A cosmic canvas on which all the brush strokes have dried. The silence isn't ominous, it's restful, like the deep exhale at the end of a story. But even in this final stillness, black holes have one more role to play. As they evaporate, they release tiny amounts of radiation. It's not much, not enough to warm your cosmic toes, but it's energy. And energy, however slight, changes things. These final flickers of radiation are the last dynamic acts in the universe. The final tiny sparks before darkness becomes absolute. When the very last black hole evaporates, that's it. No more stars, no more black holes, no more light, no more structure. And yet, we can't help but wonder, is that truly the end? Some scientists speculate about the possibility of quantum fluctuations in this far-flung future. Given infinite time, tiny random events could occur, a particle here, a particle there, perhaps even a Boltzmann brain. A self-aware consciousness flickering briefly into existence before fading again. Not because of biology, but because of randomness. These ideas aren't widely accepted, but they're not outside the realm of theoretical possibility. The universe, it seems, never stops being strange. There are also more speculative theories. Some cosmologists propose that our universe may not be alone, that it's part of a multiverse, a vast ensemble of other universes, each with its own laws of physics. Perhaps, after the death of our universe, another will be born. Perhaps black holes are gateways or seeds for new universes. These ideas remain on the theoretical frontier, but they remind us that endings are often harder to define than they seem. For now, though, what we can say with reasonable certainty is that black holes will outlast everything else we know. They are the final sentinels of time, holding their silence long after the stars have gone out. Their lives span not just epochs, but entire eras of the universe. It's strange to think that the most violent objects in the universe are also its most enduring. That something born from the death of a star could become a guardian of cosmic history. That something as heavy and powerful as a black hole could leave the universe not with a bang, but with a gentle fading sigh. If you were a traveller, an eternal observer somehow immune to time, you could watch the entire life cycle of the universe. You'd see stars born and die, galaxies collide, civilizations rise and fall. And then, long after the last candle has gone out, you'd still be watching the black holes, waiting, listening, until one final particle of radiation drifts into the void. And then, perhaps, you'd close your eyes too. Black holes, those sleeping giants, do not roar as they vanish. They do not demand attention. They do not fear the dark. They simply persist, quietly, calmly, until the end. And maybe, just maybe, that's the real lesson here. That strength doesn't always shout. That endurance can be saint. That even in the vast emptiness of space, something as unassuming as gravity can leave behind a legacy of structure, balance, and a beauty. So the next time you look up at the stars and feel small, remember, even the giants sleep. And when they do it in peace. And so we return from our quiet journey across time and gravity, having drifted through the lives of black holes, these cosmic giants that slumber in silence and shape the very structure of the universe. We've seen them born from the death of stars, watched them quietly govern galaxies, and imagined their eventual, almost imperceptible fade into darkness. From violent beginnings to tranquil endings, black holes are not destroyers but keepers of cosmic order, guardians of time, gravity, and the strange beauty of a universe always in motion. They are not chaos, they are calm. Not monsters, but mysteries. And now, as your eyes grow heavier and your breath slower, perhaps you found a kind of peace in their stillness. The universe, it turns out, has its quiet places too. So tell me again, where are you listening from tonight? Is it early morning, a midnight drift, or the very edge of sleep? What time is it on your little corner of this spinning world? If you've enjoyed this slow voyage through time and space, I'd be grateful if you'd leave a like or subscribe to The Sleepy Scientist. It's a small ripple of encouragement that helps this channel reach others, wherever they are in the galaxy. And if by chance you're still awake after all this, well, I hope the story was interesting enough to hold your attention, but not so thrilling that it kept you from your rest. And if you've already drifted off, that's perfectly fine too. Until next time, dear traveller, sleep softly and dream deeply of stars.